All right, thanks, Tim. All right, my name is Jason Mitchell. I work for ATI in the 3D Application Research Group, and I'm going to talk a little bit today about shader models, particularly ones that you haven't seen much of in the past, the ones that you're going to kind of see coming online in the coming year, and hopefully point out things that you're not familiar with and that you're going to run into as you start to adopt more advanced shading models than are currently available. Naturally, I'll divide this along the lines of vertex and pixel shaders. On the vertex shader area, I'll talk about flow control in particular, and then in the pixel shader level, we'll talk about sort of the 2x and the 3.0 models. There's not going to be any discussion of 1x pixel shaders in any detail. Now, it's important to think about shader models as existing sort of along this continuum, and potentially sort of being the tiers that you use for scalability in your engine. In particular, if you look at in the past, we had our first generation shaders, the PS1.x shaders and the VS1.1 shaders. Fixed point pixel processing and very short programs that were generally written in assembly. In the next generation, we moved to floating point pixel pipelines with longer programs that are generally written in a high-level shading language, and of course also additional targets, PS2.0, PS2B, which is one you're kind of hearing about for the first time now, and I'll go about talking about that, and of course PS2A as well. And then there's two models, two compile targets in the vertex shader realm in the 2.0 time frame, which gives you more constant store, longer programs, that sort of thing, but also some flow control, which is kind of nice. And then coming online in the coming year, you'll see the third generation of shading models, the PS3.0 and VS3.0 models. These, again, give you access to longer programs. Dynamic flow control makes its way down into the pixel shader, not just at the vertex shader. Just in case you're confused as to kind of where you are currently. Naturally, your PC developers, at least PC developers, possibly PC and console developers, you have to deploy your titles on a very wide range of platform, right? Your users have a large number of video cards. I know Valve did a really interesting sample. I hope most of you have seen this, just sampling their user base recently. It's something they have available, 500,000 users, more than that, to get a sense of kind of the breadth of the platform it is that they're deploying their content onto. And even for that sort of thinned down population of gamer, it's a pretty wide thing. Oftentimes, game developers will target different generations of DirectX and just sort of make their life easy and break it down into discrete tiers. We're starting to see shader-only games in development and see developers target the different shader models as their tiers, particularly given the long life of DirectX 9. We're not really on that sort of once-a-year cadence right now for DirectX releases. One thing that was new in DirectX 9 was the addition of capability bits in addition to just the base shader version to distinguish the differences between the different devices that ship. So if you look at, for example, something might support the PS2A compile target for pixel shaders, but what that means is that the version is PS2.0, but there's a bunch of interesting caps that are set as well, which extend that model. And I'm going to go into what each of those different caps means. So you have this sort of set of structure in your D3D9 caps structure that has those bits in it. In 3.0, the good news is those kind of there's not a lot of fine-grained caps like that. You just have a single value to look for the maximum program length in 3.0, which is nice. And also, you don't have to really keep track of, if I see this cap, I'm on this kind of device. We work with the HLSL compiler team in the D3DX team at Microsoft. All the hardware vendors do, and they're able to release their SDK at a different frequency than DirectX, which is really key, right? And so you can actually query this entry point, D3DX get pixel shader profile or D3DX get vertex shader profile, and determine what the profile is. I use the terms profiles and compile targets kind of interchangeably here. And I know it seems a little bit messy, but the fact is there's really not that many different ones. If you look at the next slide here, you'll see that whenever a device ships, it may or may not essentially need a new compile target to sort of hit it head-on through the DirectX APIs. Each target is defined, like I said, by a base shader version and some set of caps that goes with it. The existing compile targets you see there, in the vertex shader realm, you've got VS11, and then you've got 2.0 and 2A, and then there's the upcoming VS3.0 model. At the pixel shader level, you have all those 1.x compile target. Well, those are models and compile targets. And then the PS2 realm, you have the PS2 base sort of shader model and compile target, and then there's the 2B and 2A that go beyond that, and then 3.0 coming up. The differences between the VS2.0 and 2A compile targets or profiles are the number of temporary registers that are available, and also the addition of dynamic flow control and predication in the VS2A model. I'll go into detail about what those things mean. Just generally moving to VS2.0 and 2A together, you get access to more registers and also a set of additional registers, these integer and Boolean registers, which are what you use to control the flow of execution through the code. And so the goal of vertex shader flow control is to ideally reduce the number of shader permutations that you have to deal with. Ideally, you'll be able to write a smaller number of shaders and then manage the flow of execution through those small number of shaders with a small set of bools and loop registers and things like that. So you don't have to manage as many. Code size, reduction is a goal of this. Obviously, if you have flow control, you can, have loops and subroutines and things like that, and you'll have smaller code. It turns out this is actually harder. If you know anything about compilers, it's not a surprise. It's harder for us to optimize that kind of thing, and there is a lot of optimization going on in the HLSL compiler and in the drivers. It's also important to draw the distinction between static and dynamic flow control. Static flow control is based solely on constant data. And so what that means is every pixel or vertex in a given draw call will take the same path of execution through that program. Dynamic flow control, the decisions on the if-else, which branches and which code paths to take through your code, can be based on data that's read in. So in the vertex shader land, it can actually be based on a vertex component. And so what that means is different vertices in a mesh, different vertices in the same draw call can go down different code paths. The flow control instructions that exist in the sort of the virtual machines that are defined, the assembly level, are an if-else end-if construct, a couple flavors of loops, and call and return instructions for subroutines. The conditionals are pretty simple. You have a simple if-else end-if, and these are based on the bank of Boolean registers. At the assembly level, you get this very simple kind of syntax, like you see in the bottom code snip there. And then here's a little code snip. It might be easier if you look at your slide packets there to see what's going on. It's not really that important to what the details of what this code does, but the idea is that in the inner sort of part of this shader, there's this if b specular. Now it turns out that variable is a Boolean declared at global scope, so that's something that's going to show up in a C register, a constant register that's settable from outside the shader via that set register routine. And so what that means is that the resulting assembly is going to look something like this, where we check to see the value. In this case, it turns out it's B0 that corresponds to B specular. And you can conditionally jump over this code. Now, this code is going to be jumped over for every vertex that is drawn for a given draw call. Right? All the vertices in a given draw call will take this path because that's a static Boolean. There are a couple of different kinds of loops and some restrictions on how they have to coexist with the other flow control instructions. You have kind of a for loop with your iteration counts and step sizes and so on. And then there's also a repeat loop, which is a little more flexible. And the repeat is actually the one that you see the compiler spit out most of the time. Now, the D3DX HLSL compiler has some restrictions on the types of for loops that you can write, which will generate flow control. So for example, on today, if you can write flow control, you can write a for loop in your code and compile it for a VS11 compile target, and it'll work. What will happen is it'll work if it's a known constant. It'll unroll that code. If you really want to generate an actual loop in the ASM, then you're going to have to use this flavor of for loop, like this exact flavor. You can substitute like I in the end, but the rest of it has to be the same. So that's how you hit the flow control using the HLSL compiler currently. So that's a good little tidbit to keep in mind if you really want to generate that kind of code. So here's a simple example of a static HLSL loop, just looping over a number of lights, and with that for loop of that exact flavor, and then you actually end up with this resulting assembly code here on the current HLSL compiler, where you repeat that code for each, in this case, directional diffuse light. Subroutines. This is sort of a virtual machine description here. They can call forward. They can be called inside of a loop, and you have access to the loop counter in there. There are some rules with regard to nesting. One thing that's interesting, though, is subroutines are not generated by the current HLSL compiler. You cannot generate a call return code, those instructions at all currently if you're starting from HLSL source. All functions are inlined. And to be honest, with current content, this doesn't really concern us that much. The only kind of case that we as hardware vendors really would want to see subroutines used is if there's actual pressure on code size, if we can't store programs. It turns out that if it's straight line code, it's actually a lot easier for us to optimize it anyways. Okay, so that was static flow control. Dynamic flow control, as I mentioned before, is different. This is something that can be based upon data that's read in from, say, a vertex component. And there's another set of instructions here. You get some ifs and breaks that are based on just the usual kind of greater than, less than type tests. Now, the HLSL compiler has a set of heuristics which will determine whether it'll actually generate this stuff. So if you have some HLSL code and some if-elses and things that are based upon data that's computed, that would naturally generate a dynamic flow control construct down at the virtual machine level, it may or may not generate these kinds of instructions in the resulting assembly. And that's based on some things like the number of variables that get changed by the code block that it is that you're trying to skip over, just how long that is in terms of instructions, the kinds of instructions that are in there, and so on. And I'll get to the reasons why there's kind of that funny heuristic in a minute when I talk about parallelism. Now, as software developers, I've heard suggestions from a lot of people on this kind of thing, and there's sort of a ton of obvious, as software developers, you guys kind of see these obvious early out opportunities for shaders. Skipping, skinning based on a particular bone if you see the weight is 0. If the light attenuates out to 0, don't do the rest of the lighting computation. If it's on the back side of something, if your Lambertian term is not positive, if a pixel's fully fogged, just things like that where you can just drop out a bunch of shader computation. Those are obvious things to optimize. Here's an example of that. This is actually the same code snippet as before. You see that little B specular thing inside there, which was a static flow control. But on the outside, this outer if that we're looking at now, you have if the n.l is greater than 0. So that is looking for the non-negative Lambertian term. And so if this vertex is on the back side of the object relative to the light, you will skip over the rest of the lighting code there. And so this particular case, because the code inside there that you would skip over is complex enough, the HLSL compiler will generate an if LT instruction up there. So that's one of those dynamic flow control instructions you see in the code. And so that will conditionally jump over all that computation based on whether the Lambertian term is non-negative. Now, one thing that's very important for you to keep in mind is that you're not writing code on a CPU. There's a reason we can beat a CPU at graphics tasks running at a fraction of the frequencies, right? And we're running at much lower clock frequencies than CPUs, but we can do particular graphics tasks much faster, and that's because we take advantage of the parallel nature of graphics. And the fact that we don't have to do different things for different vertices and different things for different pixels as they're going in lockstep down the pipeline is huge. It is important for you to remember, even though the programming models don't necessarily look like this, that there are many shader units executing in parallel, and they're generally on the same instruction. With dynamic flow control, you're asking us to go down different code paths for different things that are in flight, and this is an issue. This is kind of why it takes a number of hardware generations for us to get to this point to where it may be worth it. It's not always a performance win. If you have a lot of, say, intermingled data, let's say your triangles on your object are very not stripified or anything, like they're very disorganized in terms of how they exist in your vertex buffer and then how the hardware is going to process them, and you do this case where you're looking for n.l, well, every other triangle is going to have a different answer on the n.l thing. And so you're basically constantly going to be having triangles that are in flight that are taking different branches down, through the shader execution. And that's an issue, and it's something that you're going to want to keep in mind as you do optimizations using dynamic flow control in your code. I'm by no means telling you not to use dynamic flow control, but I am just making you aware of this issue. And in fact, this is the reason why those heuristics exist in the HLSL compiler, is to essentially get around cases where you're going to force yourself, into a case where you just don't want to be as far as this parallelism goes. Predication is kind of one way around this at a hardware implementation level. It's effectively a method of conditionally executing code on a per component basis. It's kind of a conditional write mask. And that allows you to essentially execute straight line code, but kind of mask off the results of each of the instructions based on, say, that condition. So, for example, you could execute, essentially all your vertices could execute both the n.l greater than 0 and the n.l less than or equal to 0 case, but not generate results for the appropriate instruction. So it'll actually end up being, in that case, can be kind of similar to just doing straight line code with selecting results at the end. For short code sequences, it can actually be faster than flow control. You'll find the HLSL compiler does not generate predication. It just generates if-else type constructs in its output. And the reason for this is because it's much easier for hardware vendors to map if-else constructs to predication. Any hardware vendor is free to build a machine that uses predication, and it's very easy to map if-else constructs onto that effectively. These are kind of details that probably a lot of developers don't really necessarily need to get into. But if you find yourself having, interesting performance when you thought you were doing an optimization, this could potentially be why in the coming years. Now moving on to VS3.0, it's basically like VS2.0 with all of the caps as far as the programming model is concerned. The programs are generally longer, and there's more temps. The input and output registers, the way you can access those is a little different. You can actually index into some of those. And one really cool thing, of course, in VS3.0 is that you can access textures through this TextLDL instruction. Skip that. Like I said, a very cool feature of VS3.0 is that the vertex shaders can sample texture maps. This has obvious applications like displacement mapping, large off-chip matrix palettes, so I don't have to listen to you guys complain about constant store anymore. You can never satisfy all developers. Everybody's always going to have a character that has too many bones, right? So just put them in a texture and index into that like your matrix palette instead. And just generally cycling data that you've processed in the rasterizer back into the vertex engine. This is huge. If you've read any of the scientific computing papers from SIGGRAPH the last several years, people have a lot of applications for processing meshes, let's say using the rasterizer and then sending those column pixels, but send them back in as vertices later on. Just basically, once you can complete that cycle, there's a huge amount of applications that are opened up. Okay, I'm going to kind of go quickly here because we're running a little bit long. So now we've covered vertex shader models. I'm going to move on to the pixel shaders. The pixel shader HLSL compile targets that are available for the sort of 2.0 base vertex shader programming model are the PS2O target, the PS2B target, and the PS2A target. They're sort of written in one order, and they're alphabetically a different order. They're alphabetically the order in which they came out on the market, but they're sort of listed in the order in the chart in which they sort of order of sophistication. So, the 2.0 model you're probably very familiar with, in that your instruction count sort of a total of 96 instructions, where that can be up to 64 ALU and up to 32 texture. You have 12 temps, 4 levels of dependency, and none of the other optional caps are set. PS2B is very similar to that programming model, but the program length is much longer. It's 512. And you have access to 32 temporary registers. Other than that, the programming model is just the same as 2.0. PS2A goes beyond those. The programming length is also 512. The temps there's 22 temps that the PS2A sort of the compiler will use when compiling for the PS2A compile target. There's no limit on the level of levels of dependency for PS2A pixel shaders, and all the rest of those caps are set. Arbitrary swizzles, it should be obvious what that means. Basically, all that swizzling stuff you can do with the vertex shader, which is totally freely just very flexible. You can do that at the pixel shader level. That predication stuff that I discussed earlier, you can do that at the pixel level. There are some static flow control instructions, and you also have gradient instructions as well. And I'll discuss some of that more as I discuss PS3.0. PS3.0 also has, of course, longer programs, 512 minimum, dynamic flow control, access to these couple of sort of read-only registers, vface and vpause, and also this concept of centroid interpolation, which Sim discussed some already today. It's also interesting to note that centroid interpolation can be used on PS2.x whatever devices as well as of the DirectX 9.0C runtime. So that's actually a runtime rev that's going to be coming out from Microsoft in the future, and that will enable you to use centroid on PS2.0 devices. And I believe that's capped because not all PS2.0 devices support that. A really interesting thing to keep in mind when you're writing this, it's cool to have flow control, and it's cool to think of the things that you can do. But when you're writing sort of any kind of, let's say pixel shader, to do any kind of procedural texture generation, or even just let's say you want to simply blend between a couple of textures based on some condition. Maybe not think of that as procedural, but you are making kind of a conditional decision. You are causing a high frequency component to that signal, right? When we're rasterizing, we're effectively sampling your signal, right? Your signal is your pixel shader. And if you're not going to anti-alias sort of based on the sampling rate, then you can get some really funky aliasing. I mean, there's obviously large amounts of shader sampling hardware that's out there designed to do filtering, which is the anti-aliasing of this kind of signal that the raster is sampling by definition. So this is something to really keep in mind. You can go back 15 years in RenderMan course notes from SIGGRAPH and read upon for 15 years worth of the lore of this kind of stuff in the offline rendering world. There's a large body of information. And the offline guys spend a lot of time thinking about how to anti-alias procedural shaders. Sim talked about this also briefly. In the hardware world, we compute these derivatives. We just do it sort of naturally as a part of our LOD computations when we're going to go select the proper MIP level and filter your textures and that sort of thing. In the PS2.0 2A compile target, that is a PS2.0 part that has the proper cap set, and of course in PS3.0 you have access to these instructions. They're called DSX and DSY in the HLSL syntax. That actually gives you back those derivatives, and they're actually differences. They're the differences of those values for the neighboring pixels in a 2x2 region. That's how they're actually computed, and they're for the center points. Now, with dynamic flow control, because neighboring pixels can take different paths through the shader, you could imagine that one pixel right next to the other might go through a place that computes an LOD, or rather one computes a value that you want to take a difference of and one doesn't. And so thinking about taking that first difference between the values computed by neighboring pixel shaders may not make sense because the one pixel went through a different code path and just didn't compute that value. And so it's kind of nonsensical. And now it turns out that we can build into the HLSL programming model certain rules about where texture sampling and texture derivative computation instructions are allowed. That is, they're not allowed inside of dynamic flow control. And this might sound like a cop-out by hardware guys that don't want to build something hard, but it turns out the RenderMan does this as well. This is just inherently a hard issue to deal with in a renderer. Just a couple more things, and then we're gonna take a quick break for water and coffee. I want to try and stay on schedule here and get through this. Otherwise, we're going to be toast. There are these read-only registers, the vFace register, that can tell you whether the thing you're rasterizing was front or back facing, which is kind of cool. You can do like two-sided lighting operations and stuff down there. It appears as a plus or a -1 in HLSL. And there's also screen space position. Just the X and Y components of that register are populated. So now I just have one more quick thing before we take our break. And I know Centroid is a confusing thing, and I know Sim discussed it, but I kind of want to go over it one more time to kind of help you grok this. It's when you're multi-sample anti-aliasing, some pixels are partially covered. The shader is run once per pixel, and interpolated quantities are generally evaluated at that center point, which may lie outside the primitive. And so depending on the syntax, the sort of actual meaning of that interpolator, you may or may not have visual artifacts. As Sim said, this has been around for a while, and only some people have complained because it only generates visual artifacts for certain sort of semantic meanings of your interpolators, right? Now, centroid interpolation evaluates the interpolated quantity at the centroid of the covered samples. And so you really want to think of this as a property of an interpolator. It's kind of an interpolation mode. In the syntax, you tag an interpolator as being centroid interpolated. And so semantically, you will know in advance, or at least discover it during development, that certain interpolators should use centroid. So if we look at the center pixel in this diagram here, you'll see that one has 2 of its samples covered, and the center is not covered. And so we're going to zoom in on just that one pixel here. So this is just that one pixel. And you'll see that what the hardware will do is it'll compute this centroid here between those 2 samples. And that's the location that the shader will see to use it from sampling a texture, or if that was an interpolated color, or that kind of thing. And so we've found this to be useful for light map paging, texture atlasing, it goes by as well, where Sim discussed how you could potentially sample from outside the page that you really intended because of this issue. And Centroid can help snap you back inside the correct page. Interpolating certain light vectors and basis vectors. Our demo team has run into this a lot. They've been using this for I guess quite a while now. Starting with R300, we had this mode, and they've discovered they've really needed to use this quite a bit. I think primarily because they use multi-sampling all the time, and not all of you guys do. I highly encourage you guys to do that more during development. Now, how do you use it? It's pretty simple. There's a little syntax you can use to tag your declarators for texture coordinate iterators, both at the HLSL and at the ASM levels. Okay, so we've just kind of finished our morning session here. I covered vertex and pixel shader models that you'll be seeing in the coming year. Sim talked about multi-sample anti-aliasing. So now let's go take a quick coffee, water break, and come on back in for the optimization materials. Thanks.